Hey guys, it's Miss Rainey. Welcome back to Chemical Foundations. In this part of our video, we are going to be looking at measurement with precision and accuracy, and then significant figures in reading instruments and in calculations. Are you guys ready to get started? Oh, I hope so, because here we go. Okay, so we're starting with measurement with precision and accuracy. So first of all, measurement is a quantitative observation that always consists of a number and a unit. For every measurement you use, you need a number and you need a unit. Those units become excessively important as we go through. You need to know exactly what you're talking about, not just how many of the thing that there are. But those measurements can be accurate or precise. So we'll start with accuracy. Accuracy, is the correctness. I can spell correctness. There it is. Or the agreement. Let's see. Of a measurement with a value. Sorry, with the true value. So agreement of a measurement with the true value or the accepted value. It is how close you are to the right answer. So that is my accuracy. How close you are to what the right answer is supposed to be, or how correct you are. As opposed to, say, precision. So precision is the reproducibility. Of a measurement. Let's try this again. Oh my goodness, I got this. Or the agreement of a measurement with the other measurements. That is how close you are to all of your other answers. So let's highlight that part right here. Agreement with the others. Then we have different types of errors. So your answer can be accurate or it can be precise, but if it's got an error in it, so there's different kinds of errors. We can have a random error where we have a different error every time. It could be high or it could be low. It's just a different error every time, as opposed to a systematic error where you have the same error every time. Every time. So your random error could be high, could be low, could be who knows what, where your systematic error is the same error every single time. A lot of times you will see a science teacher with a dartboard and you're throwing darts in the dartboard, and then how accurate is this dart and this dart and this one? But in chemistry, we tried to avoid throwing darts across our lab. Instead, we take data with lab measurements. So let's look at what that actually looks like rather than just a dartboard. So we are going to get several trials worth of data in some experiments. So in this experiment, we are trying to say, let's say, find the mass of a particular substance. So we have the true mass or the accepted value for mass. So the scientific community agrees that the mass of this particular thing is 10.00 grams. So you weigh the thing 4 different times with 4 different trials. And so then your average of all your trials is 10.07. But notice that some of them are much higher and some of them are much lower. This is a random error, because some of your errors are high, some of your errors are low, which means that you are not precise. Because precision is the reproducibility or agreement of one measurement with another, and these measurements do not agree with each other. So these values are not precise. In this case, for a random error, you're probably doing some sort of lab procedure wrong, and you need to reevaluate your whole thing, reevaluate your entire process, because sometimes you're doing it one way and sometimes you're doing it another. That's different from this second trial. So again, we say the true mass is exactly 10, and the average is 9.79, so it's probably not 100% accurate, but what I do see is that it is precise. This is the same error every single time. Every single time. It's slightly below what the true mass is supposed to be. So this is a systematic error. We actually like a systematic error in chemistry because we can say we are doing the right procedure, but somehow it's always coming off just a little bit in the wrong direction, so I can check what might be making my mass low every single time. Maybe my balance is off and it's always reading 0.2 grams too small or something. So it's kind of easier to fix a systematic error because I can tell it's just a thing that's always going to be lowering the mass. So now let's look at this beautiful data. To me, this looks like it is both accurate and precise. It looks to me like it is both accurate and precise because the average is really close to my true average and all of my numbers are all very close together. But it's kind of hard to say which one of these is most accurate. Now, this one's obviously more accurate than my other two, but in my other two, my averages were different. One of them was 10.07 and the other one was 9.79. So which one of those was more accurate? For that, you're going to be looking at percent error. So for your percent error calculation, it is your measured value. So that would be, say, 10.03 or 9.99 minus your accepted value. So that would be your 10.00 divided by your accepted. I like to think of percent error as a phone company, A, T, and T. That is your actual that you measured in your lab minus the theoretical, what it was supposed to be, divided by your theoretical. So if I do AT&T, my actual minus my theoretical divided by my theoretical times 100 to make it a percent. If you're doing a chemistry lab where you're trying to create some sort of product, then you might find your percentage yield, which is just your A over T, your actual yield divided by your theoretical yield. It's just a different way of calculating error. Instead of how far off you are, it is how far on you are. All right, so that is precision and accuracy. Next, we've got significant figures. Significant figures are the digits used in determining the precision of a measurement, not the magnitude. And it feels weird because a number like a billion seems significant, but not in this case because we're not looking at how big or small. A number like a billion only has one significant figure because it only has one digit of precision. So we have to figure out how to count significant figures because a billion seems significant, but it's not necessarily in this case. So to count significant figures, we need to count the different, we need to know how to count different types of integers. So we've got non-zero integers, like say the number 789. I just said 789 and I wrote 489. Either way, that is 3 significant figures because all of the non-zero integers are always significant. If I had something like 4.872, that would be 4 significant figures because I've got all of these numbers are non-zeros. The zeros is where it gets tricky. So you can have captive zeros, that is zeros stuck between other integers, like 709. That zero is stuck between 2 non-zero integers, so that would be 3. Or if I had a billion, or let's make it smaller, 1,002. Those zeros are stuck, so that would be 4. If we have leading zeros, that is the zeros that come before the numbers, so 0.74. These leading zeros are never significant. They are not at all significant. So in 0.74, we've only got 2 significant figures. If I had 0.0035, that is only 2 significant figures. The numbers, zeros that come before the non-zero integers are never significant. Whereas if they are trailing zeros, so trailing zeros are the zeros that come after the non-zero integers, they are significant when there is a decimal point, and they are not significant when there is not a decimal point. So if I do have a decimal point like this, then I am going to count those zeros, and this has 4 significant figures. But if I do not have a decimal, then that 0 at the end is not going to be significant, and I only have 2 significant figures. And then the last type is an exact or a counting number, and so by exact we're talking about a definition or a counting number. A definition, like there are exactly 12 inches in 1 foot. So 12 inches and 1 foot is a counting or a definition, so it's an infinite number of significant figures. Or if I have 18 pencils in my hand, that is an infinite number of significant figures because there are exactly 18 pencils. One of them might be shorter or one of them might be longer, but I can count physically 18 pencils, therefore it is an infinite number of significant figures. So before we give this a little practice, I've got one other way that may help you visualize significant figures. So I'm going to draw a picture here. Shout it out when you recognize what it is. Oh, let me see. What is this going to be? Oh, what is this? What is this? Oh, look, it's America. I've got Houston right here. I've got some Great Lakes up here. I've got Florida. I've got Maine. I've got all sorts of cool America. So hopefully you know about the oceans that border America. We've got the Pacific Ocean over here on the west coast, and we have the Atlantic Ocean. Atlantic over here on the east coast. And so for this, the Atlantic and Pacific are going to stand for the decimals. The Atlantic Ocean is going to stand for an absent decimal. And the Pacific Ocean is going to stand for a present decimal. So we are going to come in from the Atlantic Ocean or the Pacific Ocean and stop when we get to a non-zero integer and count everything that's left. Let me show you what that means because it kind of sounds tricky. So I'm going to put a number here in America. Let's try 789. Okay, so that number does not have a decimal. The decimal is absent. So I'm going to come in on the Atlantic Ocean side of that number, stop when I get to the first non-zero integer, count everything that's left. There are 3 numbers left. This number has 3 significant figures. If I had something like 0.789, this time there is a decimal. The decimal is present. So I'm going to come in on the Pacific Ocean side of the number and then stop when I get to the number that is not 0 and count everything that's left. So this one has 3 significant figures. There are 3 digits left after I've gotten to the first non-zero integer. So if I put another one in there, let's say 450.0. That decimal is present. So I'm coming in on the Pacific Ocean side of the number, stopping when I get to a number that's not 0 and counting everything that's left. That number has 4 significant figures. Okay, let's say I had the number, oh, I don't know, 5.20 times 10 to the 23rd, something close to a mole. I see that that decimal is present. So I'm going to come in on the Pacific Ocean side of the number and stop when I get to the number that's not 0 and count everything that's left. This number has 3. This number is weird because it's in scientific notation, but that times 10 to the 23 is the magnitude. And remember, magnitude is not significant in these calculations, only precision of the actual number. So we only count the coefficient in scientific notation. Let me put a number in there. Let's try 0.020200. 200. Okay, so then with this number, ooh, decimal's present. Stop when I get to the first one that's not 0. Count everything that's left. This number has 5. So maybe America will help you count your significant figures. So let's try a little bit of practice on your own. I want you to pause the video here and try these on your own, and then we'll come back and then unpause and then see if you got the right answer. So pause your video. Did you pause your video? And you got answers for everything? Okay, let's try them. So I've got a dozen donuts. A dozen, like I can count them. There are 12. One of them has a bite out of it, but there's still a dozen. This is an infinite number of significant figures. You're mostly not going to have to calculate with an infinite number of significant figures, but you will have to recognize an infinite number of significant figures. Here I've got a number in scientific notation. Remember, we only care about the precision, not the magnitude. So we're just looking at as if this number was 4.30. So we're going to come in on the Atlantic Ocean. Sorry, that's the Pacific Ocean side of this number because the decimal is present. There are 3 significant figures here. Then we have 100. And so this is like, oh, I had bought that stereo. It cost me $100. Did it really cost you $100, or was it $104.75? It's about $100. This has got only 1 significant figure because there is no decimal in that number. But if we were looking at it is 100.00, exactly $100, now we've got 5 significant figures. That's the difference between those two. No decimal versus a decimal. Okay, 4.020, that decimal is present. There are 4 significant figures there. 0.0032, I'm going to stop when I get to my first non-zero and count everything that's left. There's 2 here. So if I had the number 0.0320, the decimal is present. Stop when I get to my first non-zero. There are 3 left. All right, that's counting significant figures. Now let's look at significant figures when you're reading instruments, like say you're measuring something. And so in that case, we're going to use every digit given on a digital readout, such as a digital balance. But if you're measuring for yourself, say on a ruler, you're going to measure 1 place value past what is known from the measuring instrument. 1 place value past. So let's start over here with this ruler. And I'm going to zoom in on the ruler so you can see it. Sorry, let me push that in the right spot. There we go. I zoomed in. We are looking only at the top ruler here, not the bottom ruler. We'll come back to the bottom ruler. We're going to measure this thing, this piece of whatever it is, and see how long it is. And I can tell that it's somewhere between 72 and 73. So saying 72 feels like it's definitely not enough, but saying 73 feels like it's definitely too much. So I'm going to guess 1 place past. To me, that looks like it might be 72.8. Maybe to you, that looks like it's 72.9 or 72.5. And what's fun is that we can have 3 different measurements with 3 different numbers past the decimal, and all of us are going to be correct because it is it's an understanding in the scientific community that this last digit is a guess digit. So any number between, say, 72.5 to 72.9 would be a completely acceptable answer and would be completely correct. But if we had a better ruler, like this bottom ruler here, I can tell for sure it is somewhere between 72.8 and 72.9. I can tell that for sure. So 72.8 is not big enough, and 72.9 is too big. So here I might say 72.8, I don't know, 4. And you might say 72.89. Really, any of those numbers is acceptable as long as you have an extra place decimal, like to the 100th place, not just to the 10th place. So you need to have that 1 extra digit. But if we had a digital readout, like a scale, let's say, so if we had a scale and it gives us a digital number, guess what? I just get to take the number exactly as is. That's 16.43 because it says 16.43. I don't have to do anything to it. If it's a digital readout, it is exactly what it is supposed to be. So if I have to measure it myself, then it might be different. But if it's a digital readout, I get exactly what it says. Okay, so now I want you to try these on your own and see what you get. Pause your video now. I'm going to assume you paused and that you tried it on your own. And so now let's try it together. Let's start with this graduated cylinder here on the right, and then we'll go to the left. And so I can tell each one of these markings, this is 50. And so that means this is 51, 52, 53, 54. This is 55. This is 60. So what I can tell is that my mark is somewhere between 55 and 56. So maybe I'm going to go with 55.9. Maybe you went with 56.0. That's totally fine. We are guessing this one digit past, only one digit past. 55.95 is not it. We can't guess that many, but we can guess just to one digit past to the tenths place because this measuring instrument is measured to the ones place. So I get one digit past. So let's look at this thermometer. So within this thermometer, and I know it's a thermometer because it says degrees Celsius right there. All right, so for my degrees Celsius, let me make my thing a little bit bigger here. I can tell down here that this is 19. We want the bottom of the meniscus, not the top of the meniscus. So we are not measuring from the top. We are measuring from the bottom here. And so now looking at the bottom of this blue line, it looks like it may be right at 19 or maybe just above 19. And so then let me see how they're all marked. This is 18.2. And this is 18.4, 18.6, 18.8. And so I've got one place past my decimal. And so here I'm going to guess that this is 19.05. I am going to put one place past the decimal there. And I'm sorry, 2 places past the decimal there because my measuring instrument is measuring to one place past the decimal. So I can read the lines that are one place past the decimal. So I'm going to guess the second place past the decimal. So here I have 19.05. So hopefully at this point you have noticed a problem, and my problem is my units. Every single measurement has a number and a unit. If you did not put milliliters there and degrees Celsius there, something is wrong. So make sure you have units with your numbers. Okay, let's try one more. Ooh, 2 more. So what we've got is a beaker here. And so this beaker I see 40 obviously, and then 50. So my number is between 40 and 50. And so it's giving me the tens place. I get to guess the ones place. Let's make this 43 milliliters. But if you said 42 milliliters, that's totally fine. Or if you said 44 milliliters, that's also totally fine, as long as you have one and only one place past the decimal. But what if it's a digital thermometer? It says 24.8 degrees Celsius. Then the answer is 24.8 degrees Celsius. No guessing, it just is exactly what it is. So that was measuring with measuring instruments, but we also want to think about when we're calculating, because we'll do a whole lot of calculating here in chemistry. So when we're doing calculations, we're going to keep all the digits throughout the calculation. We're only going to round when we get to the end. But there's different types of rounding rules depending on if you're adding and subtracting or if you're multiplying and dividing. So let's start with adding and subtracting. When we're adding and subtracting, we're going to round our answer to the least number of decimal places. That is the tens place or the ones place or the hundredths place. How many places past the decimal? So if I have something like 2.345 with 3 digits past the decimal, and 0.07 with 2 digits past the decimal, and 2.9975 with 4 digits past the decimal. The least number of places past the decimal is my 2 places past the decimal, 2 digits past. And so 2 digits past is the hundredths place. DTHS, the hundredths place. And so then my answer is going to round to the hundredths place because the least is the hundredths place. Here I've got the tenths and I've got the thousandths. The smallest of those is the tenths, so my answer is going to round to the tenths place when I am adding or subtracting. That's different from multiplying or dividing. When you are multiplying or dividing, we're rounding to the least number of total significant figures, not the least number of place values. And so here, since we're counting total significant figures, 4.56 has 3, 1.4 has 2. The smallest of these is 2, so I'm going to take my answer and round it to 2. And then in my next one, 2.0035 has 5, 3.20 has 3. 3 is the smaller of these, so I'm going to round my answer to 3 digits past the decimal. So now it's your turn to try it. I've mixed addition, subtraction, and multiplication division within the same problem, so make sure you're paying attention to both types of rules. Pause the video now so you can try it on your own. All right, I'm going to hope that you did, and now we're going to work them together. We're going to start with order of operations, that is 5.489 minus 5.01 gives me 0.479. The rule of thumb we're looking at here, this is addition subtraction. So we are looking at places past the decimal. This goes to the thousandths, this goes to the tenths. So my answer here is going to round to the tenths place. That's 0.47. To the tenths place. But I'm only going to round when I get to the end. So I'm going to leave the entire 0.479 in my calculator, but I'm going to remember that my answer rounds to the tenths place. So now order of operations says I'm also going to do my multiplying. So I'm going to take that 0.479 times 6.78 times 5.903, and I get 19.1707 without rounding. So how does rounding change that? When I'm doing the multiplication, my second part, I see 3 total digits, 4 total digits, and this one only has 2 total digits because I rounded it to the tenths place. So my answer is going to have only 2 total digits. So my rounded answer is just plain 19. That seems weird. It feels weird because none of the numbers in my problem had 2 significant figures, but my answer does because that's how it rounded as we went through. So let's look at the next one. I've got order of operations says I should do this subtraction first. 1.002 minus 0.999 gives me 0.003. I'm looking at my places past the decimal. All of these have 3 places past the decimal. Sorry, both of them do. So my final answer has 3 places past the decimal, which is totally appropriate and correct. Now I'm going to take that number, divide it by 3.754, and I get a number that is 0.000799915. That's what my calculator says. So my second order of operations was division. Now I'm looking at total significant figures, not places past the decimal. 0.003 has 1 significant figure. 3.754 has 4 significant figures. The least of these is 1. So I'm going to round my answer to 1 significant figure. That is the first digit that's not a 0. So then this becomes 0.0008 because the 9915 rounds up. You could also write this as 8 times 10 to the negative 4. You cannot write 8.0 times 10 to the 4. That gives it 2 significant figures. And we don't want 2 significant figures, we want only 1. So there you are, significant figures in calculations and in measurements and accuracy and precision. Please join me next time for our next video. Have a good day, guys.